most of the countries also has changed reference systems, and now they use reference systems datums based on GNSS. I will go to that, but you know, it's not very. I hope that it's not very complicated, but this figure just try to show that all the different components nowadays that can be used to do space techniques that are using for helping us to understand the Earth. So we have not only GPS, but we have another techniques, like on the left, you have all these different techniques, and also we have satellites doing, like, for instance, gravimetry. And with that we can create different problems. So we can create the position and velocities. We can monitor the sea level, although in Uzbekistan that is not a major issue, but in many countries sea level is very important. But for instance, we also can monitor the water storage and the variations in the water storage, and that is a very important issue in Uzbekistan. And also the geohazards like volcanoes, earthquakes. So all these can be put together at a global scale to help monitor our Earth. And I was talking about reference frames, and I like to show this figure because nowadays a major problem is also has to be with the reference systems. Of course, this is not true. This is just a image that tries to show what can happen when different people are using different systems. And if I have more, like in many countries, that has been one of the problems. It's this update of the reference system. And more important, sometimes that has to be a very consistent reference or a very accurate reference system, is to have a common reference system. Because otherwise we can face, of course not like this, because this is very stupid, but we can face problems when we want to know, for instance, the area of a piece of land, or we want to like design a road or a pipeline. So we need to ensure that we are using always the same reference system. And for that, in fact, GPS, GNSS and other techniques are helping a lot. Because in the past, each country was using different local reference systems. So Portugal, I can give the example of, like, Portugal was using one reference system, and Spain, that is just nearby, was using another reference system. And those reference systems were normally not compatible. And I know, for instance, here in Uzbekistan also was using another issue was Uzbekistan was using, if I know correctly, if I'm wrong, please tell me. But as I remember, like for the horizontal reference system you are using was also tied to the system from Soviet Union, from the Soviet, and even the vertical component was coming from the Baltic. So that, you know, and that also creates problem of quality, because it's extending all over many kilometers, and that creates problems with the reference. Nowadays, using space geodetic techniques, normally mostly GNSS, but also other techniques like VLBI, SLR. So there is this network of stations all over the world that help me to define a common reference system for that can be used by anyone in any part of the world. The latest realization is IQRF 2020, and basically, you know, it has this distribution all over the world. And it was like in the past. In the past, also, we can think this. In the past, we just have like national system. So we have these points. Yes. We have a point, you know, in the past, like the reference system of the countries were defined by these points on the top of the mountains. And the control points that we have to observe from one to each other. Yes, please.
Can you give more details about what is the VLBI, SLR, quarries?
Oh, okay. I didn't show VLBI. I have a slide for that, but I don't have here. So let me explain. Yes. VLBI, SLR, you can see, and the doors. Okay, are another techniques to get positioning. For instance, the Doris system, is similar to GNSS, but it works the other way around. You could station the GNSS. I didn't explain much, but how it works GNSS. For people that don't, GNSS basically we have the satellites up there. And they are sending a signals to us. And I have my receiver here. That can be a very good receiver, or can be like my watch. My watch, I have inside, it has a GPS, it acquires signals. Nowadays it can be so small like this. And it gets the signals from the satellites. And since I know where the satellites are, because the satellites send the signals and also send information that tells me where the satellites are. And you know, if I measure the distance from the satellite to my receiver, can be this one or can be one like you saw outside. Knowing the distance, and if I have several satellites, I can know where I am.
It's GNSS.
Yes, with GNSS. So the system are sending so they are sending it, and because the distance, I can compute the distance. Why? Because the signals that is sent by the satellite, it travels at speed of light. So the signal comes at speed of light, but I know when the satellite sends the signal and when I receive the signal. So the time times velocity gives my distance. So I know the distance, measuring I can measure the distance between the satellite and where I am. And when I use several satellites at the same time, I can know where I am. I need to measure at least 4 satellites. But nowadays, I can see like 60 or more satellites at the same time. Not just 4, like 60, 70. And what I can do, I can receive all this information and just try to get the best position for all that at the same time. That is how GPS works. Doris, the first that I'm talking, is a French. Doris is a French system. It was developed by France, and it works the other way around. I'm in the ground where I am that transmit the signals, and there are satellites. The satellites that receive the signals, and it can do the other way around to know where I am. So the system is like GPS, but the opposite. The problem with Doris is that you have to send all this information. You have to send this information because you send the signal from the ground, it goes to the satellites, and after the satellites transmit to France. And it's in France that they compute the positions of the station. So it's real dependent of it's a scientific system. It's not, for instance, I cannot use Doris to do positioning like for surveying or anything, because it's fixed position, it's stations all the time. Okay? SLR is called satellite laser ranging. And just for you know how it works, it's also, there are satellites coming here, and there are ground stations also. And I imagine it's like I have a gun, and I'm shooting, or you know, like lasers. I'm sending like this. Okay. Okay, the satellite is there, and but you know, the satellite is moving. So I can start to sending the laser. The laser, the signal goes there and returns, and with that I can measure also the distance to the satellite. Measuring these to different satellites, I also can know where I am. But again, I apologize, I could show in my computer. I didn't put here, but this is also okay. But maybe I can. What here? Yeah. Let me go back. Okay. Yeah. You can see there. Oops. Sorry. Okay. You see there? This is SLR. So it's a lot. It's kind of this room. So I also cannot take with me and measure any place. And finally, just to explain all, VLBI. It's receiving signals from quasars from space. So it's getting the signal from space, and if I have two stations, I need two stations for VLBI. And the two stations receive the signal at the same time, I can know the baseline between the stations. So, like VLBI, as you can see, is these stars. So there are not many in the world, because it's these big telescopes that work. So, you know, from all these systems that I'm talking, in fact, the only one that can be used at the national level is GNSS or GPS, because all the others are just used for the definition of the global system, the international system. Okay, so we need them because they are important. Because I will not enter in details, but for the definition of the phrase global, GPS has some issues, and the other techniques can compensate those issues. And so the combination of all these techniques is what makes the global one very, very accurate. So, but for national level, we go to the GNSS. But okay, out of this for that now the GPS or GNSS. This is IGS. IGS is an international organization. It's called international. IGS means International GNSS Service. And it's an organization for people all over the world that what they do, they maintain this global reference network, global network of reference stations. And another thing that they do very, very important is also to compute orbit, to correct orbits. Because when I'm doing in real time I'm getting the orbits that I got. It's, you know, when I say orbits, it's orbits. It's the position where the satellites are. And I need to know that to know my position. But in real time I get just an estimation where they are at a certain point. But using this network of stations, I can after recompute that orbits and get better, what we call better orbits or final orbits. And those orbits normally are need to be used to get the best positioning possible. And we use that after for instance, for the control points or for the reference points that we really need to have the best position possible. If I really want to go to few millimeters to know the position, and nowadays I can go, you know, nowadays we will know the distance between any of these points with a very, like 1, 2, 3 millimeters ever. So I can know the distance between a station in Uzbekistan and a station in Portugal, or in the United States, or in Australia, or any place in the world with real, very, 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 like 1 millimeter. We are talking about this. This is nothing. It is amazing. And because of that, we can use also these stations for many other applications, like the scientific applications that I mentioned before. So I will show after more details about this application, but this is just for you to have an idea of this global frame. Oh, sorry, the other way around. Okay, and one of the very important, and I'll go now a little more to details, is about the tectonic plates, because it's also very important to understand that is one issue that we have. Is that the point, all these points, they are not fixed. They move in time. All points in the world move in time. You know, they are not exactly. If a point is today in the equator, just to have an idea, in the line of the equator, there is a point there. Next year will not be there. Will be already several centimeters from the equator. Because of what? Because of the tectonic plates. Because all of us are moving. Okay. The difference is that sometimes we are moving together. Because this is like blocks, plates. So for instance, if all of us are in Eurasia, all the points in Eurasia are moving with some relative motion, but basically all are moving together. It's like here. All of you are there, imagine. We are all moving. But if I move with respect to you. But all of you are not moving with respect to each other. Okay? So that helps us to understand, and in many countries, for instance, that helps us also to use the points, the control points, the CORS stations. Okay, and what is CORS stations? CORS means continuous operating reference stations. So it's permanent stations that we install and stay there, acquiring data every day. And with that, I can use nowadays these stations to know how the plates move, and I can use those stations, for instance, for technical purposes like reference surveying, like using for surveying land measurement, measure of lands, cadastral applications. I can use all of these because I can, they are not moving in the countries one with respect to the others. And the other countries, they are moving, and we are going to look at that. So, how I can see that the stations move? It's as I'm saying, imagine this is a CORS, a continuous operating reference station. And I install the station. So I install the station today, and I'm acquiring the data. And every day I can see where, I can compute where the station is on the planet, on the globe. I can every day get the position of the station. So if I get today, I'm here. I get tomorrow, I'm here. I'm here. Okay, every day I'm moving. After some time, I can see how I'm moving. I can see how I'm moving, and in each direction I'm moving, and with which speed I'm moving. So, for instance, for studies trying to identify deformations between points, what I can do is estimate all the velocities of my stations and see how they move one with respect to the others. So, and this can be done, and this is just an example of how we compute, how we get the velocity. So, what I can, as I was explaining, I can get day one every day. And so what we do, and when I saw that we are processing stations, one of the things is every day we use a software that is called GPX. We use this software, and every day we get the solution for each day. And we use this global network that I showed before, and with this global network, I know where the stations are with respect to the global reference frame in day one, day two, and so on. And with that, I can after, if I know all the points, I can know where they were. I can try to compute the velocity. And this is just an example of several stations on the world and how they move on the Earth. So, for instance, we can see like in Europe, we are in Europe, they were moving like north to northeast. And around 25 millimeters, 2.5 centimeters per year. So the velocity, like in Europe, is about that. Here, and I will show more results, it's a little bit more to east. Here in you can see, you know, your position. So, for instance, in Pacific, stations in Pacific is moving more faster than in Eurasia. You can see that the velocities are much faster, and that is the reason why like in Japan and the areas in Pacific, there are very large earthquakes. Why? Because they are moving very fast, so they create very big tensions and they create very large earthquakes because of this. All these velocities, because you know, imagine this is like cars. If we are moving all at the same speed, there is no problems. But if one car is moving faster than the other, they crash one to each other. Or when two cars are moving one against each other. So if one car is moving in this direction, another car is moving in this direction, of course there is a crash. And this is what happens on the plate boundaries. The plate boundaries the earthquakes is like earthquakes is the consequence of the crash that the plate boundaries they have running against each other. Or in the other places is because it's opening. So if in one place they are crashed, the other place they are opening. But when they open, they also create tensions, and that tensions is also create earthquakes. Okay, so I will just give two examples here. I will start with what I'm talking. I'm giving the first example with Bhutan. Bhutan is just located in north of India, and in the plate boundary between India, you can, right? You know, the Indian plate, it's like, we have here Eurasia, this is Eurasia, this was India. And India, imagine, wasn't really like a car. Eurasia was moving like this, and India came and boom, just one against the other. And because of that, it created the Himalayas. And the Himalayas are the consequence of this crash, and it's still, nowadays it's still building up. Even here in Uzbekistan, most of the deformation is caused also because of this crash, let's say, the convergence of India against Eurasia. So what we can do, I'm just giving this example of how we can use the CORS stations to measure these deformations. And in this case, in Bhutan, there was installed 6 permanent stations, CORS, and we could measure how they move on the Earth. And that, you can see here, they are moving, you know, all to northeast. So the movement, imagine, when I show this, what is that? It's like, imagine, if I was in the center of the Earth, it's like when we are here and we are looking to the stars, we could think the same like this. I'm in here, the center of the Earth, and I could see the CORS moving in time. And they are moving to northeast. But okay, that doesn't help me to understand much what is going on. But I can do another thing. I can just say, okay, how they move. But how they move against, like for instance, Eurasia. How is the movement with respect to Eurasia? And I can see that is also more to north. It's like Russia is here and these stations are moving like this. So this is the movement of the stations. And that helps me to understand, you know, and if you see the scale is still like 2 centimeters per year. So you can really see how it is collapsing. But I also can do the other way around. I can to how they move with respect then to the people in Bhutan. Because they will, you know, it's getting real. Of course, this will be millions of years, so we don't need to worry so much. So this is the example. But I would like to show you, because I think it's more interesting for you, about Uzbekistan. What is the, in Uzbekistan. So what I was looking and I just used the stations that are public available. So I went to pick up the stations from IGS, and I went to compute for these stations. And here in Uzbekistan there are two stations, and I use also the stations in Kyrgyzstan, just so we have an idea how it moves. So, okay, there are two, as I say, there were two stations, Kitab and Tashkent. As you can see there, there's two stations, and I compute, the velocities. To explain this figure, this is latitude, longitude, and vertical. So the latitude is how it moves to north. So how it moves to north. The longitude is how it moves to east, and the vertical how it moves on the vertical. And you know, the black points, the blacks are daily solutions. So these stations are very old. These already have been installed many years ago, 98 and 2002. So we already have like more than 20 years of data. So I went to collect all the existing data and I processed. I got a solution every day. So every day, this black points is solutions for every day. And with that, I try to fit the best line through all these solutions. And I got the velocities. I got the velocities how they move to north. I got the velocities how they move to east, and also the vertical. And for instance, you can see that they're not like Kitab or Tashkent. Tashkent moves like 4 millimeters per year to north, about 27 millimeters to east. And there is some uplift, not much, 0.3 millimeters per year in the vertical. So it's going a little bit up. And what we can do with this? Okay, I can make similar plots like I did for Bhutan. So this is for these stations how they move. So basically you can see they move not much to north, it's more the movement is to east for the stations. So I plot for all these public stations that for my GS I compute that for all these stations. But this is just how they move, you know, again on the earth. Now I can also say, okay, and if they were in Eurasia, so I remove the velocity of the Eurasia for these stations, so I can compute the relative motion with respect to Eurasia. And what we get here, as you can see, that in the eastern part of Uzbekistan and also in Kyrgyzstan, where I got also substations, you can see that they are moving now with respect to Eurasia, and Eurasia is the northern part, in the north. They move around 1-2 millimeters per year. Okay, what is the importance of this? The importance of this is, with this I can try to quantify what is the hazard. What is the hazard on the, because if they are moving, I can, one with respect to the other, I can try to quantify how much stress is accumulating on the earth. So I can somehow help me to understand what is the probability there will be like an earthquake in the future. And where, and if I have more stations, I can know better where there can be, where there are more stress or less stress. So that is the reason, one of the reasons to do these calculations. And that is the reason why also now the Center for Advanced Technologies are installing this network of stations in the country. And with this network and also the additional stations that the Ministry of Emergency is installing, it will be possible to know better what are the areas that are more active or where there are more deformation. Of course, now what we have also to do, or you have to do, is wait. Because we will need time to compute the velocities, how they move. It takes some, you know, to do this fitting, I need a period of time. So, but, okay, as I'm saying many times, if you don't start, we cannot finish. So the only way to finish is to start. Oh, sorry, I'm going back. Yeah. So this basically is also the example here for Tashkent. I don't know, I'm talking too much, so I will try to go fast now, because I also still want to talk about my company. So I just want to show you another example that can also, of what the importance of all these networks of stations. How important are these networks? And this is an example. It's already old, because it was from the earthquake in Japan that you probably remember in 2011. A very large earthquake that also caused a tsunami, as you can see. And, you know, Japan has a very dense network of CORS stations. There are about 1,200 stations distributed in the country. Very dense network. And, oops, okay. Can you just, And this is what happened during the day of the earthquake. You see, this is the position of the stations, and look what happened. There was an earthquake, and there was this displacement. When, after the earthquake. So, and please see the scale. The scale was 1 meter. So there were several meters of movement. You know, it's like I'm here, there is earthquake, and there was this incoming several meters to special. But I can see, and I also, but we also can see the waves going through. Can you just put again, please? You see, nothing is only some noise, nothing. Earthquake, and now, boom, and you see the waves, look, the waves going through. Like, you know, the shaking, it was like boom, and boom, like this, until past. And after, you know, and far away, there was just shaking, but nearby there was big displacements moving. So this is just to show the importance of this. I will just give a last example very quickly. This was in Portugal. In Portugal we have some islands that are in the boundary, in the middle of Atlantic, that are between Eurasia, North America, and Africa. And 2 years ago there was a seismic crisis, and there was a lot of earthquakes starting in one small island. That island, it's in the middle. It's called some shores. It's difficult to. I cannot point, but it's just there in the middle of the different islands. It's a very long and thin island, but it starts to get a lot of earthquakes. It started on the March 19. During more than 1 month, there were many earthquakes. And we also, I show this figure just to see that sometimes this can be complemented with other techniques, like INSAR. INSAR is also a technique that allows us to see deformations. And we could see that most of the deformation was in the northern part of the island. And in addition, we use also the CORS stations. So there was a network of permanent stations, and with that stations we could see how was the deformation occurring. And just so you have an idea, the important message here is that the deformation normally is like 4 or 5 millimeters per year, not more. But in 1 month, there was like 1.5 centimeters, 3 times more than the entire year. So it just moved, everything moved like 3 times that normally is moving. So we can use this again. We can use this again for what? For a warning system also. Be careful. Be careful. This is creating tension. So these were some of the examples that I would like to show that is connect what you are doing here. Now, I will just move to my company and see what we are also doing. So give just a quick example before I finish. My company, I just create my company, and my company basically it's in my university. So it's a private company, but the headquarters is in the university because it's innovation. What we do more is innovation and research. So we are focused also on create and do consultation and services, products in geodesy, geomatics, all these areas. And it's a new company, but because of all our experience, we already have done projects in more than 20 countries in the last years. And again, just to give an example of our recent installations of stations. So one of the areas that we do is reinstalling and maintaining networks. And again, this is the slides because we rely on the experience that also my research group has done. One of the important things that we have been done is like the definition of the reference systems that I explained before. So we have been working in many countries, and we are contributing or creating the new reference systems for surveying, for technical applications in several of these countries. In fact, it's also missing 1 or 2. And also not just for horizontal component, but also for the vertical component. For instance, we have created sometimes I joke and I say when was now last year the World Cup. During the World Cup, the football, the field needs to be horizontal. The football field, and we have contributed for that because we have defined the vertical datum of Qatar. So we know, if to make it the field, the soccer fields horizontal, and also I think Seychelles, Bhutan, Maldives. These were also projects that we have worked with the vertical components for using because in the past the vertical is a very important subject, because in the past people were to define the vertical datum, they were using basically leveling. You do leveling all over the country.
Levels you mean? Just levels you mean? Level equipment?
With level, yeah, but you have to go to know the vertical position of any point here in the example of Uzbekistan. You need to, in the past you need to do with leveling lines, you need to go and take from one known point until there. Nowadays, what most of the country are doing is creating what is called a joint model. And I go there, any point in the country, I go there with my GPS. I know what. I apologize if this is too technical, but it's just to know the vertical, because the problem, and without entering much details, GPS, the vertical of a country is based on geoid. And what is the geoid? Basically is the surface that define the sea level. So we try to define the sea level, and we know, when I say that, like, correct me, here is about 350 meters. The height, the vertical here in Tashkent is 350.
500.
500?
Yes.
Okay. Yeah, but when I say that it's 500, it's with respect to the sea level. How I know that here is 500? In the past, how I knew that was here is 500? Because many years ago, some people went from the Baltic Sea and start to Baltic Sea 0, because it's sea level, and start to bring the height until here. But of course that creates a lot of errors. So it's 500 something. Another approach is that I go with GPS and I get my vertical position. But GPS doesn't give the vertical position with respect to the sea level. It gives the vertical position with respect to what is called ellipsoid. And is a geometric position. Basically, is the distance to the center of the Earth, removed from the geoid. The geoid, probably many of you already hear, normally is the WGS 84. So we remove that and we know the distance to the ellipsoid. GPS gives me the distance to the ellipsoid, that is this vertical, that it is WGS 84. But to use the orthometric, which is called orthometric position, that is with respect to sea level, I need to convert from the GPS, the height given by the GPS to the vertical position orthometric with respect to the sea level. And to do that, nowadays, people, what they do is using geoid ondulation models. So I have a model for the entire country, and if I'm here, what I do, I come here, I get my position with respect to the ellipsoid, the GPS, I use the GPS, I get the vertical position with respect to the GPS, and after I apply this model to get the vertical position with respect to the geoid, to the sea level. That is the vertical position that we should use, for instance, for many applications for surveying, because these differences are not parallel. I will not enter in details. If someone wants to discuss more, I will be very happy, but otherwise it will take a long time. But this is the most efficient way to do nowadays vertical, to know the vertical. And for most of the applications, it's important to say that leveling is still necessary. Leveling is still necessary when I do like a pipeline. But for instance, when I'm doing cadastre or I'm doing other, just do some surveying to define where I should make a road. Not when I do the road, just when I'm planning to do the road. I don't need leveling. I should use normal. I can use these geoid models that are much more efficient and even most cases more accurate. And this is just examples of the countries where already they are applying these models to get the vertical positions using GPS. Okay, let me also say that we are also we are here, and I have to. This is also one of the reasons is that MIRASPACO is representing Septentrio in many markets, and basically on the scientific receivers and for geodetic applications. So we are collaborating with Septentrio, helping with the installation of representing their products. In particular, as I say, for reference stations, for CORS. These are the different products. I'm not here to sell equipment, so I'm not going in much detail, but I would like to say that in this respect, Septentrio has been considered one of the, it's very advanced receivers particularly for reference frames and for also some scientific applications. So you have the normal stations, reference stations like it's called Polar RX5, but they also have special equipment just for ionospheric monitoring or for timing. That is also another important application of GNSS. I will not enter in details on this, but just to say, and now, just selling a little bit, I really think that the quality price of these equipments are real very good, and for me, in this respect, has been good to this collaboration, because it's when you have products that are real good, it's also good. It's easier to distribute them and to sell them. Sorry again, and another aspect, and also just to finalize, it's also about software. So we have developed, and we started many years ago developing this particular software for monitoring networks of and why we did that? For two reasons. Because we were working many times in countries where still the communications are not the best. Nowadays everything is improving a lot, but we already started many years ago where communications were real, internet was still an issue. An issue to be robust, and an issue on the price. And the other reason to develop this was also the cost of many products. And I don't I'm not talking bad about other people, but like Leica, as an example, Leica and Trimble, they are very good products. Real reliable. They have many people working on those products, and they have been developing for many years. They are very good. But they have two problems, in my point of view. First, they are focused on big markets, like Europe, America, where there are very good network, internet. So when it goes to another places, it's difficult sometimes, an issue to work, and the other issue is they are very costly. They are real, some of these softwares are very costly, so we just decide to develop our own software. Basically it manage all the network, so we can tell you how it is the status of each station. There's many functionalities. Or one important thing is that we don't work. Although, for instance, as I say, we have a good relation with Septentrio, we can work with any other brand. So we have equipment. We also manage different any brand. We just need to know how to communicate with those equipments. And also it's based just on the web server. So basically we install the software in one server, but after I can, if I want to go, if I have the permissions, I can just pick up my mobile and check the network. Because I can, using the internet, I can just go. Of course, I need to be authorized to do that. So I need to, only authorized users can access the network, but if I have the authorization, I can check what is going on, just using my mobile in any part of the world. What we do a lot of times, in fact, supporting our clients. Okay, we just get all this information in real time, so we are knowing what is the status in real time. And another feature is the caster. Not for instance, not for like for the caster is not important, but for instance for mapping agencies, for many users, an important feature is to be able to transmit RTK corrections in real time. So our software also allows any user to get correct real-time corrections for their surveying applications. I'm just end up with another product that we also developed that we call MIRASPACO. This software can be used now to compute the positions. So basically, if I go to the field and I acquire data for control points, this is not for real time. This is for control points. If I want to know, I can just acquire the data on the field, and after I can upload the file to be processed. The file is processed and can send back to you your position, not in the IQRF, because like in Uzbekistan, as an example, Uzbekistan doesn't use IQRF as national reference system. Use a national reference system. So what we do, we convert the position from IQRF to the national system. So this system only works, this software only works in countries where it is authorized to work. We don't offer this service in countries where we don't have authorization from the mapping agency to do this. It has to be it's an agreement. This has to be an agreement with the national, with the government of the country. Okay, so CAT network and the new network and is real, so Ramat, thank you. Obrigado.